Thank you very much. It was a very interesting presentation. Of course, it's funny that we're doing very similar things from different angles. So that most of the things you're doing are things that either we have been doing or we have been considering from the point of view of diffusion models and generalization. This is the funny things I was saying before, that what for associative networks is a problem, for us is the solution, and the other way around.
Yes.
What is the solution for you, for us is the problem. Although I sit a bit in the middle. I feel like I find both things interesting. But implicitly, so what we want actually, like in generative modeling, is to not be able to retrieve the individual data point, exactly because they will, because instead of their fixed point will actually merge together in larger structures.
Yes.
So
I have a question for you. I have a project that I've been thinking about for some time, but I'm curious to know, given that you've been thinking so much about this juxtaposition between memorization and generalization, I'd be curious to tell you about what I've been thinking about and hear your thoughts. Yeah. So you're probably familiar with hallucinations in both diffusion models and language models. These hallucinations seem to be things that are like plausible, but they seem to be like combinations that don't make any sense. And I've been trying to think about whether or not one might use either tools from associative memory or from generative modeling to try and sorry, I'm not saying this well. I'm interested in trying to know, could one identify a possible origin of hallucinations in generative models based on ideas that we've discussed here?
I think so. The problem is that I think there is a bit of a social confound here. So I don't think that because people want generalization generative model, right?
Yes.
For example, if I ask ChatGPT to tell me a story, I would like the story to be new and not to be a complete reproduction of the training set.
Yes.
The reason why I wouldn't consider it an hallucination is because me, as a user, I ask for something fictional.
Yes.
From the point of view of the model, any piece of scientific text is equally fictional, which could, like in Borges, can contain both fictional and real citation. In some sense, it's not much in the math, though. It's in the way we relate. The generative model doesn't have a notion of reality, you know? So if you make it not generalized, that will be useless, right? It will just sample from the training set. But it's difficult to say, oh, you have to generalize here, but not there.
Yes. But I am thinking to myself, so two things. One, I agree with you that there's a social construct, but I think in other cases there are more clear-cut examples where there is no sort of ambiguity. For concreteness, oftentimes people complain. So for example, text. Like this text, something that looks this screwed up, I would assume has never occurred in the training data set. Moreover, I think another example is, especially with humans, like oftentimes diffusion models will give them 6 or 7 fingers.
Yeah.
And while I agree with you about, say, for example, generating text, I think that's a very good example. In other cases, I don't think that 8-fingered humans are anywhere in the training data set. So it seems to me like there are more clear-cut examples. It's probably a spectrum, of course, but there probably are more clear-cut examples of hallucinations.
Yeah, but in some sense, it's good, right? It's good that our model are not trying to memorize. So it's there are situations in which, like the text, right? I mean, diffusion models empirically, I don't think this is very understood theoretically. I think this would be a great project to study, but empirically, they tend to be quite local. Diffusion models tend to look a lot in local surroundings. I think that's one of the reasons why they generalize well, because they pay attention to global patterns, but they're also very sensitive to local surrounding. Writing is difficult for the diffusion model because in some sense, at some point, it will make a decision of what the letters are, and it will work by its surrounding. And at some point, from its surrounding, it's difficult to correct a wrong decision. And then you get a flip of letters. And I feel the same with fingers. There are a lot of things together, and you can locally get a good finger here, locally get a good finger here. And then, like in an Escher painting, it becomes difficult to actually join them. But in some sense, I think that we do know that as training or diffusion model progresses, these things tend to gradually be solved. So in that sense, I'm not sure we need to do something. Like if you look at hands now, and hands last year, they got substantially better. So right now, a decent fraction of the hands you will get from DALL-E 3 are anatomically accurate. It's a big improvement for like a couple of years ago.
How do you imagine that they solve that? Is that, I mean, I don't know if anything has been publicly said about DALL-E 3, but how did they actually solve that?
I mean, I don't know specifically, they're not open, but what I don't think that there is anything special. It could be that they use some classifier for screening. That's always possible. And the reason is they have so many classifier for avoiding toxic material that they could have also got lazy and use classifier for screening, and you will never know unless because that's something you can always do. But my guess is just more data and bigger architecture. I think that as far as you give the model enough data, it will learn correctly. Just fingers and letters are a bit difficult because locally it's easy to make them look consistent, and then you make a kind of a small mistake, you know. But like also the text, I mean, look at the text that you got here. That's for the first iterations of DALL-E, the text was an absolute mess. Now the text is you can see what is you can read it. There will be misspelling, but you can read it. You know.
Yeah. The reason, so I agree that one hypothesis is scale up data, perhaps better architectures. These problems will go away as you do better and more training. Possibly, I'm willing to buy that. The reason why I'm maybe a little bit skeptical is because at least in like the classic Hopfield network, we know that spurious patterns exist. And we know that no matter how much data or how good of an energy function you choose, those spurious patterns will always exist. And in fact, as you put more data, they get worse.
Yeah, but we want spurious pattern. Without spurious pattern, we don't have generalization. That's actually, we don't want...
Yes and no. Like some spurious patterns I could imagine would be a good generalization, but others could be like incoherent patterns.
Yeah, but it's a bit in your mind, right? Like there are a lot of things. Like if you're asking like to have the universe and we'll put stars in different location, you wouldn't notice if the letters. It just our brain is very focused on telling written text apart, and then we can see any small mistake. While for other kind of things like the peaks of those mountains, you want the variability, but for our brain, it's not to say, oh, this is not. So in some, I do think what. I do think that you are close to the point. I just think that the specific situation that we find where the errors are in some sense tell more about our brain and our capacity to discriminate things than the model itself. Not 100%, okay? But for writing, for example, if we did not know how to read, those writing will look perfect at the moment.
Yes.
And we don't know how to read mountain peaks or so.
Yeah. No, that makes perfect sense.
I just think we have to be careful to not try to solve a problem that is not really a problem, and sometimes the solution is worse than the problem. So I think the big risk that we are going to have in the future is to push the models towards memorization. And so
wait, say more about, you think that a problem will be pushing them towards memorization?
Well, so we do know that the optimum, so again, in theory, the exact given the data set, the optimum of the diffusion model is the modern Hopfield net with that energy function, which we know fully memorizes the data, at least for zero temperature.
Okay, I was about to say,
Yeah, exactly. So you can stop diffusion earlier, and that's the trick. I mean, that's something we are investigating right now, and just is coming from the literature, that actually you can still get generalization in the empirical score by stopping diffusion earlier or by some sort of regularization. Like if you look in the dynamic phase paper, it will mention like that. And there is something funky happening in the network. The network tends to not want to memorize, tends to regularize the memorization phase. But the more data you give, we do know that if we keep training on the same data for long enough, and we have the network has enough parameter, eventually we'll memorize.
Yeah.
And when it starts memorizing, it loses variability. Basically, it stop creating something new, and we start simply reproducing the data. Actually, what we're studying with Gianluigi, this is work in progress, but it's not even a black and white situation.
Okay.
Well, so what we're currently studying is that the way we see memorization is not really from generalization to full data reproduction, but is dimensionality loss.
Okay. What does dimensionality loss mean?
Well, so imagine that the data lives in some subdimensional manifold, right? Usually in images, you will have some kind of lower dimensional structure that is embedded in the pixel space. As memorization, so now consider the pure memorization case. The pure memorization case is zero dimensional because the minima are series of points, okay? Yes. Generalization corresponds to a surface of minima or a hypersurface of minima.
Okay.
Okay. Now, what's in between, right? There is a situation in which the best that the generalization in which you have, like, say, d-dimensional space of possible creations, and then you have a situation in which you have zero-dimensional, in which you have zero-dimensional state of memorized point. And now what's happening in between, right? And what we conjecture and which we are finding experimentally is that you gradually lose dimensions. The more dimensions you lose, the less freedom you have until you lost all your dimension and you're only left with your training point. And that's the full memorization phase.
Makes sense.
Like the condensation phase in the dynamic phase paper. So you can have a situation in which you have generalization, but you are lost, but you kind of lost variability in the data because some direction have been lost. In the sense, the data points in those direction kind of condensated and then became kind of isolated and independent.
That makes perfect sense. Yes, thank you for explaining.
I mean, this is stuff we're currently investigating. Hopefully, we will be able to output something soon. But I think it's a quite a fascinating phenomenon. Now, my point is that there is a lot of very interesting math that separate memory and generation, and I think that these are really two sides of the same coins. Yeah, again, the only thing I think we should be careful to check our own biases. In the sense that sometimes it would be. Maybe this is the point of alignment, but there is a mathematical structure there, and we want the model to generate, right? We don't want the model to memorize, and there are some specific things that we don't want it to generate, but they're very cultural. For example, we don't want to generate fake citations because we know citations are a serious thing, but generate fake, but if it's a very cultural thing, right? You don't want fake scientific articles, but you want like fake stories, if it's like a Lord of the Ring kind of fiction. And imagine, put yourself in the point of view of a model that has been exposed to the human world in this way, and it needs to understand a very higher order kind of. So I think that, I mean, I do see that what a lot of people are doing nowadays in practice is that they use post hoc things, right? If you don't want to generate toxic material, often you put classifiers at the end and you will clean them out. You can be more fancy. You can use these classifiers to guide the diffusion, and maybe they do this in stable in OpenAI. Maybe they don't. I don't know. There are pros and cons, but if you have a classifier, you can also guide the diffusion away. So, and that will become close to Hopfield. In fact, we are working with some people who are trying to use Hopfield ideas exactly for, let's say, kind of for erasing memories or for stealing things away from. So these are things that I think Hopfield people can really contribute a lot. So I feel that for all these things that are a bit cultural, like what is a toxic image or what is confabulation or hallucination and what is generation, I think you really need to tell the model explicitly, often using classifier and by specific. And I mean, you can do that quite easily. Classifiers fit very nicely in diffusion. So let's say you train a classifier. Okay, you label text and you label whether hallucinate or not. Okay, and now you need to give the very cultural human feedback. Okay, this is generation, this is hallucination. Okay, because it's not allowed to make up a false scientific work, but it's allowed to make up a false story about my grandfather. Okay. Except if it's the grandfather of someone who is known, and then it's not allowed to do. So there are a lot of things that are allowed and not allowed, right? So you need human feedback. You need the supervision. But once you have, then you can train a classifier to distinguish what is hallucination and what is not. It's not in the math, or at least if it's in the math, it's a math beyond our understanding, because it's really our culture. But at that point, once you have the classifier, you can guide the diffusion, either screen things afterwards, just the boring option, or you can even guide the diffusion to, basically you are modifying the energy, and something would be very familiar for you. Yeah, just basically removing the part of the energy that you don't want there. And so given the supervision, then you can do it. And then basically you are removing parts of the landscape that you don't want to generate while preserving, hopefully, and that's the part that you want to generate, and when you want creativity. So you don't need to do that postdoc. It's very nice that basically you can, every time you have a classifier, you can add that additional term to the score, which basically is conditional generation. So it's always a form of conditional. So the kind of things that you were saying about context dependent, that's what it is. It's always that. And you can do that in multiple ways, using a classifier or training with conditional signals, some supervised conditional signal. But basically what you're always doing is conditioning, and basically you can condition to stay out of some places or to get more often in some places, and so on. And yeah, I think there's a lot of exciting research to be done there. And so I'm sorry if I sounded dismissive for the.
No, not at all. This is great. I love this. I'm taking notes. Yes.
It's just mostly that I think we should be aware of when there is something in the math, like maybe the model. For example, and sometimes something cultural are in the math, right? In our symmetry breaking paper, we show that if you undersample, you will get most white faces when you generate on Salabay. Okay.
Okay. Yeah.
In sometimes, but is it the cultural bias? Well, yeah, maybe, but there's not that much of. There is a bias in the data set, which is distribution, but there is also the fact that if you undersample a diffusion model, you enhance biases in the sense that you will oversample large classes and undersample small classes.
Okay.
And the reason is a diffusion model is like a kind of series of routes that go from the beginning of diffusion to the end. And if you move into much rough steps, you can miss the little exits, which you just skip them, and then you just go along the main road. So the point of the symmetry breakings is that the symmetry breakings are points when decisions are made. And what we show in the paper is that if you skip the part, if your sampler does not actually sample correctly the symmetry breaking section, you lose the diversity because you skip the decision. So this is a situation in which there is something fundamental in the math that give you loss of diversities, and that has, of course, serious cultural significance. But it's something that is you don't need to tell the model to be more diverse. Of course, obviously, like the data is the data. The model will reproduce the data.
Yeah.
But as a lot of people complain, and it is true, and honestly I was a bit skeptical in the beginning, but it is true. If the model tend to, if it's not, and diffusion model made a big progress, but generative models, if they're not executed correctly, amplify biases.
Yeah.
They enlarge classes that are overrepresented.
Yeah. This is okay. Very
Okay. But so this is the maybe if I can, this is the kind of problem. The amplification of bias is the kind of problem that you solve simply by training better and by understanding the math better, simply because it's just statistics at the end. Your goal is to reproduce the statistic of, obviously, if your goal is to violate the statistic of the data, then you need external supervision, right?
Yeah.
If your goal is to respect the statistic of the data, then actually you need to understand the model and train it well. So there are two classes of problem. Once you want the model to train better, and the other you want to kind of align the model, right? So you want to tell the model to do something that is different from what would be normally expected if you just try to reproduce the data. Yes, Gabriel, did you want to?
Yeah, so because you were talking about hallucinations, I was just thinking like the problem of hallucination is not really of the generative model itself, right? It's mostly about the way you condition information, right? Because if you see, for example, in the images from DALI, I mean, I think that most of the problem is the way you just click, right? Because you don't pass all the information. For example, typically the issue with the images that you get is based on particularly on the text that you want to see. And I would say that most of the time, I'm not sure exactly how they train CLIP, but I think that has to be related with the way they use how they pass the conditional information.
Yes, so, I think, yeah, I think this is.
I think that's the problem.
Yeah.
Because I think that the clip is just basically, so the mapping with the text and the images, I'm not sure if they use all the text pair with the particular image corresponding to that text. And that's why we see something weird, because it was not properly encoded in the input for the conditioning.
I think that's
what
probably.
Do you think about it?
I think that I once read a paper saying that the models, like, for example, I don't think that whatever Jolly 3 is generating based on, I don't think it actually receives the text directly. There was a paper I once read that said if you just embed the text that somebody wants inserted into the image and actually give it to the diffusion model, then it's actually perfectly capable of generating correct text.
Sure.
So yeah, I agree wholly with what you said. Yeah.
Yeah, exactly. Because in the unconditional case, I mean, they work pretty great.
Yeah.
The conditioning is just because mostly you want to condition something that maybe they never were conditioned on, and they don't have any clue of what to show.
I mean, it's variable, right? Clip works extremely well in some setting, unless it depends on data density, I feel. Like if you want to generate scientific images, it's horrible. Just try to open Bing AI and it will, if you ask for a rat with an exposed brain, there will be a human brain in the middle of the belly of the rat. It just generates some monstrosity.
Yeah.
In some sense, it's interesting, though. It definitely does not memorize it. I've never seen images like that. But in like for some things where the data is more sparse, like scientific illustration, it's very difficult to condition the model to do stuff that you want to do. Yeah, it's
to me, that example that you just offer, I completely agree. I've seen some pretty bad stuff myself. Going back to your point that you made about how like we need to distinguish between when there really is some sort of mathematical property that is genuine and true that we should understand and seek to improve versus is this a social construct, in which case that's much more nebulous. This is why I was thinking that specifically in the context of hallucinations, I'm wondering if there is a mathematical aspect to it. The specific thing that I'm thinking to myself in using this context, using this example of the rat with the brain in the belly, it's like, I'm wondering if this corresponds somehow to some sort of like weird metastable state that shouldn't exist. And what I mean by that is like, I imagine the training data set has a ton of rats, perhaps has a ton of scientific diagrams, perhaps involving rats, and then it has a huge disproportional amount of human brains.
Yeah.
And then somehow between these three minima, I have lots of data about rats, lots of data about human brains, lots of data about medical diagrams. There's somehow some sort of point in the middle that the model thinks exists, some metastable state that should not exist.
I do agree. It's certainly the case, but the problem is that also for good generation, like for the image that we are seeing at the moment, is again a metastable state that shouldn't exist in the sense that it's not in the data set.
That's I guess what I'm wondering. Like, to what extent is it possible to disentangle whether or not a metastable state should exist or shouldn't exist? Like, I could imagine that there are metastable states that depends purely on the data. Like, given the data that you have, this is the best you could possibly do. But then I could imagine other ones that have more of an architectural construction, which is like based on, like, take the modern continuous Hopfield network, based on how the energy function is defined, and given a particular training data set, together I know that certain metastable points will exist, that if I were to give you more training data, they might cease to exist. So sorry, I said I talked a lot. What I meant was, is it possible to distinguish whether or not metastable states will persist with increasing amounts of sampled data versus will disappear with increasing amounts of sampled data?
Oh, that's a very interesting thing that we will need a lot of statistical physics to figure out. That's actually that is cool. Yeah, that is true. So, I mean, assuming the limit of infinite data, there will be a manifold forming, which will correspond to the distribution of the data. But there will also be spurious structure that will appear and disappear.
Yeah.
Can you know from in advance if it's something? Yeah, that's interesting.
I think that you've helped me improve understanding of my own question. So this has been an amazing discussion. I'm very grateful for that.
Thanks.
Yes, no, thank you. I should get going, but I wanted to also briefly ask, you guys are doing tremendous, great work. I'm curious to know, we were talking about having you come present to Ela Feet's lab.
Yeah.
Okay, and I think one of Ela's, or maybe two of Ela's PhD students reached out about scheduling a time for you to come present.
Could be that I forgot to send an email. Yeah, I got. Okay. I got an email, so I will answer. Unfortunately, I've been extremely busy these days, so
totally fair. Okay. I feel like I would love to better understand the work that your group is doing, and so hearing it properly.
I would be happy to. I will respond to the email. I will respond to the email now. So.
Sounds good. The other thing to mention is the part about exacerbating bias. Initially, that's fine. I have another thought to make, but I'll send it to you via email.
Well, at this point, just finish this.
Okay, fine. My Stanford lab doesn't care that much about associative memory, and they're not super keen on generative modeling. They do all sorts of odd things. But one of the things that the lab does care a lot about is bias, and about whether or not. So the point that you were making about how in generative modeling, unless you pay close attention to the details of the math, that I don't want to say incorrectly, a suboptimally implemented model can exacerbate biases of the data.
Yeah.
I think that that's something that actually my lab would be very interested in.
If you, I think that the symmetry breaking paper will be very interesting for you guys. Yeah. So that's we have very nice results. So basically, with by using this physical intuition and changing things slightly, we can restore the diversity quite almost entirely. So that's yeah, I think it's very interesting. That's one. I was surprised that something of such a societal significance follow from such a fundamental things in the math. That is the fact that the decision is made at a specific point. There are also interesting things, like for example, when you get this oppression, black people tend to be preserved more. And the reason is quite obvious, is that they are more separated from the white. So the problem when you lose diversity is because they are absorbed. So Latinos and Asian almost disappear entirely because they're absorbed by white, which is the majority. While black tends to be reduced a bit, but not by a crazy amount. The nice thing of diffusion models that, and same for Hopfield, is fundamentally they depend on the Euclidean norm. So actually, there are while they describe a very complex things, a lot of the dynamics is actual just dot product, and because they have these Gaussian kernels. So I think that the reason black people tend to be preserved by the diffusion model is simply because they don't correlate much, just linear correlation.
Yeah, that's fascinating.
Yeah, I think this is very cool stuff, and connects with very deep physics. I mean, I don't know if you know, but the symmetry breaking phenomena are actually at
very poorly, unfortunately. Which is something
they are very famous. The most easy to understand example is a magnet. A magnet, a hot magnet does not have an external magnetic field, but it has the potential of magnetize itself. And if you cool it down, it will magnetize itself in one direction.
What does it mean to magnetize itself?
To produce an external magnetic field. If you get a permanent magnet, it will produce an external magnetic field. Okay. Now, once you have a magnet with an external magnetic field, it will point somewhere. Okay, it will point in a direction. It will have a north and a south pole. Okay.
Right.
So the magnet itself does not have the energy function of the magnet does not have a specific orientation. So it doesn't necessarily want to orient itself in any specific direction. But when you cool it down, it will start pointing in a specific direction. And this is the reason, because the energy landscape splits in a series of equally likely low energy states, and one of them will be selected by chance. So this is a spontaneous symmetry breaking. The energy of the magnet is symmetric under the direction of the magnetization, but one magnetization needs to be chosen. And therefore, you will see, if you just look at the magnet, it will look as if the magnet really likes to magnetize in a specific direction. And
what is it? Sorry, go on.
That is the same what's happening in a diffusion model. Diffusion model before sampling can potentially become anything, but it needs to make a decision, and this decision will become split into potential energy function. So when your energy function you're studying in a diffusion model depends on time, and as a time, you will transition from being a single convex shape to it will separate in different peaks, which then separate each other. Each of these separation correspond to a decision, and those are the so-called symmetry breaking that happen during the generative dynamic.
One of the things, well, first of all, thank you for explaining that to me. One of the things that I didn't quite understand, though, is that if the energy minima are have equal values, and then the system has to choose one versus the other, what is it that actually did? Is it just pure chance that determines which?
It's the noise. It's the noise at that time. So basically, it's a change of. There is a change of stability. So before you have a fixed point, before you have a convex shape, a single fixed point in the middle, which is the average of all data, and everything is mean reverting. So everything wants to go back there. It's just a quadratic potential. Okay. Everything moves around it. Then there is the stability of these fixed points start to change, and there is a critical point in which the quadratic well disappear. Okay. Because you get the quadratic approximation becomes zero. The second derivative becomes zero, and then you get flatness. Before the quadratic well stopped the fluctuation of the noise. So before of this separation, if there was noise in one direction, it would be reverted back. After, the barrier disappear and there is space.
I see.
After that, the potential will split with different minima, and then there is a very short amount of time in which a small fluctuation in the noise will actually push you in one direction, which is completely random, but it will have a huge effect
Interesting.
On your future trajectory, because after that you're going to be trapped in another well.
Yes.
And once you're trapped in a well, you cannot move much. So basically, every separation of wells will be a decision, and it comes from an amplification. It's similar in the sample of the magnet, right? In the magnet, the final orientation depends on random fluctuation in the atoms that form the magnet. Normally, those random fluctuations don't have macroscopic effects, okay? Because in the thermodynamic limit, random fluctuations are completely suppressed for a very large object, except during a criticality, during a phase transition. What is a phase transition? The phase transition is a time where random fluctuation can be amplified to have macroscopic effect.
Okay.
So in a phase transition, a random fluctuation that can start at the infinitesimally small atomic level can propagate and cascade down at the point of causing a macroscopic effect, like a magnet aligning in a specific direction. And this phenomenon is called critical instability. Basically, the material becomes so unstable that every small fluctuation will actually amplify itself.
Yeah.
So it's a kind of a violation of thermodynamics. Thermodynamics is kind of tell you that microscopic fluctuations don't matter. It's the probability concentrate. And the exception is in the critical behavior. Well, kind of there isn't as in the critical time, there is not a separation between microscale and macroscale anymore. So everything can propagate to everything. And you get very similar phenomena in the diffusion model. You get this very small time in which the system is very sensitive to the noise, and that noise ends up constraining the diffusion behavior. Now, if there are small classes that have low probability, you really need to sample the time they separate in order to get them. So if there is a small like stream of potential that leads to Asian in the group, if you skip that part, so if your discretization of the time is 2 curves, you skip that part. At that point, you have missed that separation, and you're just skipping that class altogether. So you will severely drop the diversity of your sample.
Makes sense. Yeah.
Theoretically, it's also in the dynamic phases of diffusion model, you can also they give a formula for finding where the classes will separate. So in our paper, we just look at a specific a general phase transition at the beginning, but in the new paper, you can actually, they give you a formula for finding when different classes will separate. So if you care about diversity, you can be sure to sample that specific time point, of course, at least in generative model. And then just give you, you know that you need to sample that part very carefully. And if you do, you will get substantially higher diversity. Of course, by diversity, I mean diversity in the training set. So if the training set is biased, you will never do statistics does not know of our social norm. So will not correct the proportion to the training set, but it means respect the proportion to the training set and not amplify existing
Right. Yeah. That was an excellent explanation. Thank you. One of the things, this is kind of a random question. I've always meant to delve into statistical physics, but I've never had the time. And I also don't know what the right place to start is. Do you have any sort of material that you would recommend? Is there a good place to teach myself?
It's just a lot of stuff, and there are different levels. I mean, in general, it's the nice things is that for like standard statistical physics, so you basically study with, you start at the bachelor level, right? And then the decently standard thermodynamics, statistical physics. The modern theory of statistical physics is 90% the theory of phase transition or second order phase transition, so criticality. So if you look master level courses in statistical physics, I can say, if you send me an email, I can send you a good book. And
that's what I was primarily looking for, a good book.
The theory of criticality, what I was describing here, which are also called second order phase transition, is basically 90% of modern statistical physics. It's the crown jewel of statistical physics for the more advanced material. Of course, I mean, they tend to be a bit advanced, and again, it depends how deep your interest is in the topic, you know.
Yeah.
We are also applying a lot of statistical physics together with a lot of very good physicists. So if you at some point you want to collaborate with us, you can learn from the job from also working with them. I think you will understand a lot of concepts because you reason in terms of energy. So I think everything will be quite straightforward for you.
Perhaps, but like, for example, I've never been able to successfully do a replica calculation on my own. I always need help. And so These are the sorts of things that I need to learn.
Also for replica theory, also it's not that I did study it myself. There are not even very good books because it's quite scattered around. If there are books, but there are lecture notes, I can send them to you.
Okay. Yes.
And but you can also find them by Google. Just look at there are lecture notes by Parisi and
Parisi. Okay.
Parisi is basically the founder of replica theory, and but yeah, probably you will. But yeah, it's scattered around. Again, now we're working a lot with random matrix theory, for example. It's quite connected, and they also use replica methods.
Yeah.
So, but also there, the problem with these topics that they are for people who already know it often, or they are there are some good lecture notes, but they tend to be kind of graduate material that usually propagate just are passed from supervisor to student.
Exactly. Yeah.
And not necessarily course material for a lot of things. I mean, again, I'm not an expert in any of these fields. I did study some of it, but now for most of the replica theory, we just have collaborators that are really trained on it. There is a very, I mean, a lot of this field actually come from Italy, from the school in Rome. So if you talk to Italian physicists, often they'll go.
Yeah.
Yeah. So I can send you some material, or I can also ask so people we work with for. But yeah. Also, if you want,
I will follow up with you after this then.
Yeah, and we're going to do very cool stuff directly with them. So if at some point you have some free time and you want to join us, that's probably you will learn a lot from the process. And I think it's a bit easier to learn these kind of things while you're using it for something that is useful for you. You know?
Yes. Yeah.
Because if you're not a student, I mean.
This is the problem of like I've tried looking at statistical physics courses, and oftentimes they start with the motivating problems are gases in boxes, and I'm like, I understand why they're starting there, but like this material is not particularly compelling. So working on something that was much more compelling or interesting to me, I think would be more motivating.
Well, I mean, I do think that before modern Hopfield net and now diffusion models, this is a bit of a renaissance of the statistical
100%.
physics for machine learning. I mean, for a while, I mean, of course, in the 80s and early 90s, there was most machine learning was statistical physics, like Boltzmann machine and stuff like that. But for a while, there was very little. Actually, now diffusion model is kind of a renaissance of physicists, the finding that the theory that they've been that they have been studying are actually extremely relevant. And all this memorization is basically the same that you get in random energy model, which is one of the same models that the first models that they were developed for studying this random. So the reason you have this, I don't know if you know something about random energy or the way physics of disorder system works. But basically the idea is that you have two levels. It's a kind of second order thermodynamics. You have two levels of randomness.
Okay.
Often it's called the physics of glassy systems. And the idea is that if you have a piece of glass, glass is not a crystal, or at least it's not a regular crystal. So different glasses have different structure of atomic bonding. Okay. Now, it means that two different pieces of glasses have different thermodynamics because they will have different Hamiltonians. Okay, because the Hamiltonian depend on the connection between the atoms, right? Which will be different for two different pieces of glass.
Okay.
So why do two pieces of glass look the same? Well, the reason is that, so you have two levels of variability. One, the variability in the sample. When you pick a piece of glass, the structure of the Hamiltonian will be different, and it will have its own thermodynamics. Okay. So there is what they call the quenched uncertainty, which is the uncertainty over the structure, and then they have the uncertainty due to the thermodynamic fluctuation. The physics of disorder systems, basically, it's a kind of second thermodynamic limit, which tell you that for the limit of large system, you will have a suppression not just of thermodynamic fluctuations, but also of the quenched fluctuations. So that two big pieces of glass tend to behave the same, to have the same physics, because both the thermodynamic fluctuations and this kind of structural fluctuations are suppressed. So there is kind of two statistical suppressions. Now, why is this important for machine learning? Because we worked with finite data sets.
Okay.
And a finite data set is like a piece of glass. It's okay. So you have your data distribution. It's one and unique, right? But then if you sample two different small data sets with her, you will get features that are only depending on the data, and they're not depending on the data distribution. Okay. So how can you use the physics of disorder system here? Well, by considering what's happened at the limit of large data sets is what's happened for a big piece of glass. And the idea is that the kind of randomness in the pattern of the formation of the glass is kind of suppressed. So you can understand a lot of statistical phenomena of like convergence from the point of view of thermodynamics. So a lot of the tools, therefore, it's how you study memorization, for example. Memorization is a point where on average, so basically the way that Carlo described memorization first in Hopfield network, I don't know if you know his paper, like basically you look at an individual point in the state space and you look, what is it going to be attracted the most? Is it going to be attracted the most to the very next memory, or is it going to be attracted the most to a cluster of memories that are nearby, to a manifold structure? And the answer is that it depends on time. There is a critical time where on average, the data point will be attracted more to just the next memory, memorization, or to the manifold structure itself that is still undifferentiated because there is enough smoothing to keep it together. Okay.
Yeah.
So, so you can see and this is on average of all the possible way of resum. So the point of random energy is that you look at on average what's happened for any possible data sets.
Okay.
Yeah, so most of these calculations are at the thermodynamic limit. So they look at infinite dimensional scenario, but they apply quite well to realistic scenario because we often work in very high dimension.
Right.
So in the limit of infinite many dimensions, you actually get a lot of analytical tractability. Like the replica method, usually you will use it in the thermodynamic limit. For a lot of these techniques, you will use in the thermodynamic limit. So at least I think it's clear conceptually why you want to use it, right? You want to look at the effects that the fluctuation of the finite data set, because memorization is a kind of a finite data set effect. And also the onset of generalization can be understood in terms of emergence from given the data set size, right? So in terms of a phase transition, which is not just a word, it's actually a physical phase transition that you can actually find. In this case, I think it's a first order phase of the Glassy type. So they call that like replica symmetry breaking in this case.
Okay.
So there's the kind of phase transition you get in glasses. So it's more complicated than it's again random energy models and physics of disordered systems. But I think this is right. So you could actually approach this theory from only from the point of view of memorization, machine learning, generalization, and you don't need even to interface with the physics if you don't want, in the sense that is, you don't need to actually get into gases if you don't want. Actually, there is, of course, a very nice book by Mark Mazar, which actually give a, do you know the book? Information is called.
Is this one with Andrea Montanari? This is Mazzard and Montanari.
Yeah.
Okay, this one, information physics.
Yeah, so this is a very good point. I mean, it's a bit. It's not a super easy book, but this is if you want to study these things from someone interested in machine learning, just read this book, and I think then you could need a bit more background, but you will figure it out. But it's decently self-contained.
So let me stop. I realize I've been sharing this entire time. Let me stop real quick. Okay, cool. Yes.
Mark is also the senior author of the recent paper I was talking about condensation, and we're also collaborating for this dimensionality thing. So there is a decently small number of people who are working on these topics because it's quite specialistic. But I don't know. I think you will, given the way you reason in terms of energy, I think you will pick it up decently quickly if you. I mean, of course, there is a lot of decently advanced math, but
I'm sure
also with the style of a physicist, which is most. I mean, it depends, right? Some people, it's not the kind of math because in machine learning, people often want to be very formal, you know.
Yeah. It's not what I'm interested in. Yes.
Yeah, so a lot like for the replica method, for example, I think to this date there isn't a completely formal justification. The justification, what they found that every time they had closed form solution and they got solution with the replica method, they got the same.
Yes.
But we are still not entirely sure that is. But I mean, I like this kind of math. You know, it's not much into the axiomatics. It's more about using it to understand things.
100%. Yeah.
But it could also turn you off if you really want formality. Although again, what Mark does, it's also formal, or at least we can formalize most of those things. So in that case, you get both.
Okay. I'm realizing I'm paying attention to the clock. I should probably get going. I'm so sorry to have stayed so long and kept you all, but this has been an amazing discussion. Thank you for telling me all of this, and I'll follow up with you via email. Yeah.
Okay. Good. And I will answer soon. We'll answer now to your email so that we can
Perfect. So you don't have to answer now to the email. I know you're very busy. Okay. Cool. Excellent. It was nice to meet all of you. See you all later.
See you.
Thank you so much. Bye.
that's cool.